Good morning, good afternoon, good evening. Let's get started. We left off last time looking at Z-scores, amongst other things, but that was kind of the last thing we did. You know, the standardized Z-score. Wasn't that essentially a number that would allow you to fairly compare two different groups? That's one of its uses, but it has others. Are we comfortable with how to calculate a Z-score? Would you like me to do another example just to remind you? Any preference? Okay. Suppose you had a mean of 110, a standard deviation of 15, and someone's score, we'll call that a score. Someone got a score of 130. Right, that's the raw data, right? That's what they got in some test. Who knows, the test was out of 200. The Z-score is the data, take away the mean, and it's divided by the standard deviation. Hold on a second. Right, so you're going to have to hit spacebar if you want to answer the question. So let me go back to my thing. Here we go. So in this case, person got 130, take away the mean 110, you divide it by 15, and I believe the answer is 1.33 to 2 decimal places. There's a Z-score. So far, so good, right? That's how you calculate Z-scores. Let me find a question here. So, for example, in question 6 on your homework, and this is question 6 from chapter 2, bell-shaped data. That's just another name for symmetric. And in question 6, we are told about textbooks that students spend in a year. And the mean is $540. And the standard deviation is 100. So they collected data on a lot of students, and they asked them how much they spent on textbooks. And the average was 540, and the standard deviation was 100. And then they ask us to calculate, there's 4 questions here, some Z-scores. I'll just pick my own 2. Suppose one of them was $620. Then the Z-score is going to be 620, take away the mean, divided by the standard deviation. So it's going to be 620, take away 540, all divided by 100, and that number is 0.8. Pretty straightforward kind of question. There's not a lot you can do, you know, to interpret. Before I did this question, how did I know that the Z-score was going to be a positive number of some kind? Right? How could I look at this 620 and realize that this has to be positive? This is just a way you can kind of check that you didn't screw up.
Because it's a dollar amount, it can't be negative.
The sample is greater than the mean.
Is that what you mean, Robert? Rob? That number, the sample, is bigger than the mean. Is
Yes.
that what you were? Yeah. If you mean that, I agree with you. Yes. So if this number is more than the mean, in which case, what, $540, then you know the Z-score is going to be positive. Suppose then, just for completeness sake, I did 490. Well, the Z-score for 490 would be 490, take away the mean, divided by the standard deviation. Well, 490, take away the mean. Can you see why it's going to be negative just there? That your data is, you know, smaller than mean. When you subtract them, then you're going to get a negative answer. And I believe the negative answer is, in this case, negative 0.5. I'm not even going to do a calculation for this last one. What would the z-score be if the data was 540? See, big fat 0. We good? Now I'm going to tell you some more properties about z-scores. There's lots of them. But if you take the mean and you add and subtract 3 standard deviations, don't you get an interval? And if you're outside that interval, what's special about you?
You're an outlier.
You're an outlier. So we know that test, right? Great. It's a nice thing. If the data is the same number as the mean, won't the z-score always be 0? Right. So if there was a test and the average was 90 and you got 90, your z-score is 0. Doesn't matter what the standard deviation is, your z-score is always going to be 0 if the data is the same number as whatever the mean is. That's it. Pretty minor property, but it is useful. So far, so good. Right. Let's move away from the z-scores and focus now on just means and standard deviations for a while. Can you remember we talked about this weird rule called the 68, 95, 99.7 rule? Remember that rule? Which said if the data was symmetric, right, bell-shaped, roughly symmetric, that you could make a pretty good estimate of what the data would look like. And so imagine that I have some data and it's nice and symmetric. Let's pick a question that works with. So this is an example of question 11. The numbers will be different, but the question won't be. So in question 11, the mean is 100. And at least in my question, the standard deviation is 12, right? And we are going to create a table that looks like this. What number goes right here, right at the top of the hill? What's that number my finger is pointing at?
100.
Yeah, it's the mean. It's 100.
Yeah.
Great. And then you go 1, 2, 3 this side, and you go 1, 2, 3 that side. Remember building these guys? Now, one standard deviation would be 112. Then it'd be another 12, so that's 124. Then another 12, and that's 136. So be comfortable with those 3 numbers. Now, if you take away 12, you get 88. If you take away another 12, you get 76. And if you take away another 12, you get 64. Are you happy with the other 3 numbers? Now, one of the questions that you're going to get, and I'll kind of show you it, because if I kind of answered it here, looks something like this. Do you see this is the picture, but they've gave it letters of the alphabet? Now, although you can't see my picture, wasn't D 100? Remember, that's the number. And then E would be the 112, and then 124. And then finally we finished with 136.
You're
Hey,
going the opposite
Professor,
direction.
you're gonna-
And I'm going the opposite direction. Did you all catch that deliberate
Yep.
mistake? Do any of you believe that was a deliberate mistake? Because if you do, I've got a bridge I could sell you. Does this question kind of make sense now that you've kind of seen where the numbers are coming from, right? Your numbers are going to be different from mine, but the question now, okay? Now, they ask you here, what is the variance? Now, I know that we've seen it. Okay, some weird happened there. Sorry for being distracted. Right, I think that's it. Okay, we're good. Right, back to the Scylla. Can you remember a question where they told you how to calculate the variance?
I believe the variance is the difference between the A and G, basically.
Ah, interesting. Yeah, you can actually do it that way, and nothing wrong with what you said. It just, I phrased my question badly. What you said is correct for what you thought I was getting at. Can you remember that the variance is the standard deviation squared? And if you don't, I'm telling you. So when it says what is the variance, it's the standard deviation, which is what, 12, so that'd be 144. Now, if we do what Rob was talking about, if you take this guy here and that guy, right? This 164 and that 136. If you subtract those two numbers, right? So that's basically the distance from A to G. Do you imagine that, A to G? Right. If you subtract them and divide it by 6, you would get standard deviation, which is kind of connected to what Rob was saying. But we don't need that. We just need this guy. Now I'm going to zoom back in and show you another kind of interesting property. Imagine I've got a set of data. I'll put some numbers in. This is 11. That's 121. Right. So from there to there, right? That's the smallest, the minimum. This is the maximum. And I'm not even telling you how many numbers are there, or even what they are, except that they're in that range, right? So we have a term called range. Not interquartile range, just range. And you get that by taking the maximum and subtract the minimum. In this case, 121, take away 11, and the answer is 110. Are you comfortable with how you calculate what's called the range, right? It's just the difference. You probably in English say, oh, the range is 110. That kind of tells you from start to finish there are 110 different numbers, right? Possible numbers. You can use a little formula that says this. The standard deviation is approximately. So normally in math, when something's approximate, instead of putting the equal sign, you put two little wavy lights. It's like a bent equal sign. That just means it's approximate. Not necessarily exact, but close enough that nobody cares, right? It's approximately the range, start to finish, divided by 6. Why would you divide by 6, not 2 or 4 or 44? What's the significance of the 6?
Number of different intervals.
Yeah, do you see 1, 2, 3, 1, 2, 3? Isn't there 6 standard deviations from the start to the finish? So in this case, it'd be 110 divided by 6. If I wanted to get an approximate answer to what the range is, it's about 18.3. So if someone says, I've got some data, it's a nice, hill shape, right? It's nice and symmetric, and it starts at 1 and it finishes at 21. Couldn't you do an estimate of the standard deviation by just saying, okay, 21 take away 1 is 20, 20 divided by 6. The answer is 3.3, whatever, that kind of idea. And I believe they have a question where you do that. Yeah, and the question that does this is question 10 from that homework. And the version that I've got gives me these numbers. It's bell-shaped, it tells us. It tells me the highest score was 100, and the lowest score, it told me, was 40. And it asks me to find the range, that's question A, and then to estimate the standard deviation. Well, would you agree that the range in this case is 60? And won't the standard deviation be the range divided by 6? It would be approximately 10. In this question 10, they even told you what the mean is. And the mean happens to be 71. And I never used that number anywhere in question 10. And it's a little bit distracting, isn't it? If you see a number, you think you got to use it somewhere, at least in one of the questions, you know, if it's an A, B, C, D or something, one of them's going to end up using that 71 somewhere. But actually in this question, isn't the mean of 71 totally irrelevant to the two things you're being asked? Couldn't I have rubbed that out and not told you what it was, and the answers would still be the same two numbers? So sometimes you got to look at extraneous information. Right? That's just information that is of no use to the particular situation that you're interested in, right? Couldn't I have told you that the guy who collected this data was called George? Wouldn't that be extraneous information? I don't care, doesn't help. Couldn't I have told you the interquartile range was 40? Why I would tell you that, I have no idea. But couldn't I tell you that? Wouldn't that also be extraneous information? I don't need it for these questions. I prefer they didn't give you that type of information, because it does tend to, you know, what's the word? Make you want to change what you believe is the answer. Okay, let's see what else we got. Now I'm going to return to this question and put in some more information. What percentage of the data is within one standard deviation? What percentage of the data is from 88 to 112?
68.
Okay. Now, if this whole thing is 68, doesn't that make this piece 34 and this piece 34? Does that make sense?
Right.
And normally I don't do that, but in this question that's about to come, this is going to be important. Right, now, it gets a bit messier when you do the next one. When you do two standard deviations, isn't the whole thing 95? You see that? 95?
Right.
Now, normally I would just do a big thing there, shade it all in and say that whole thing is 95. But I'm not. What I'm going to try and do is figure out how much this little piece of the pie is and how much this little piece of the pie. So that's going to be a lot more work. So
For 2.5.
Oh, interesting. Keep that number. Keep that thought. I'm not saying it's wrong, just keep it. There's a very badly drawn hill. Right, that guy's 34 and that guy's 34, right? Now, if we go to the next number, this is 95, agreed? Now, if you split it into two equal pieces, wouldn't this be half of 95 and this other side be half of 95, right? So I'm going to my calculator and we're doing 95 and I'm going to divide it by 2, and that gets you, which I think is what you were saying, doesn't that tell you that this piece here is 47.5 and this piece here is 47.5? You still with me, guys? Now, I don't want to know that that piece, right, the whole thing is 47.5. I only want to know what this little piece is. So how do I find it?
47.5 minus 34.
And that's going to get me
13.5.
13.5. Is that what you went and said earlier?
Yes,
Then you nailed it. Now, once we've done this once, you probably want to copy this and just stick it in a piece of paper and keep it handy. It's not like you're going to use it for more than a couple of questions, but for the couple of questions, you're going to need this more detailed version. It's helpful to have it. Now, there's one more guy still left, isn't there? Don't I have to find out how much these two little pieces are? Now, they're tiny, but they're still important. And so here goes. I'll start my picture again. There's the middle. There's one. There's two.
1.35.
Wow, well done. So we got to here, 76, and over here, 124. Well, it doesn't really matter. That just happens to be these numbers. And we know that entire chunk, two of them is 95%. And doesn't that make the next chunk the 99.7? If you subtract those two, right, that away from that, isn't that 4.7%? But don't you share it equally with the two pieces? So if you divide that by 2, you get 2.35%. So I'm going to go and put in 2.35. 2.35. Isn't there theoretically tiny little bits left over? And isn't the tiny bit that's left over nothing 0.3% split evenly? So there's a 0.15 and there is a 0.15. So that picture, and I'm taking out the numbers now because they're not all the other numbers at least. That's the picture, like a more detailed version of what that graph looks like, right? These pieces are 34, these pieces, and so on. So now I'm going to find that question that does this. And so this is question 13, is one of them that does this. And in question 13, you're told that the mean height, at least in my version, is 54. And that the standard deviation is 3. So being a visual kind of person, I like to draw the picture. Doesn't matter if I'm very accurate looking, I just draw my picture, right? And right in the middle, I go 54. And then I go 1 standard deviation, 57, 2 standard deviation, 60, and 3 standard deviation, 63. And then I'll go, choose another color. Then I'll go 1, 2, 3 the other side, and that's 51. That's 48, and 3, that is 45. So far, so good. Now, I've already got all these percentage guys in, but I guess it's just going to make my life easier if I transfer them across. So 34, 13.5, 2.35, and 0.15. And then for no reason except I want to, 34, 13.5, 2.35, and finish with 0.15. And then in question 13, they ask you, what is the circumference such that only 2.5% of adult males have a smaller head circumference? So if you look at this piece of the pie, which one of these numbers would be the right one to choose so only 2.5% of the people had this or smaller? And the answer I'm going to pick is 48. Can you see these two guys add up to 2.5%? And if you have a head size of 48, only 2.5% have smaller head size. So my answer to question A would be 48. Then they go and they say, what is the head circumference so that you've got like the biggest head? Well, if you're in the biggest head and it's 2.5%, you see it's 60 now? And then they say, what's the head circumference such that 16% of adult men have a larger head circumference? So if you want 16%, isn't it going to be these three pieces? 16. Great. Which is what, 57. Can I say what head circumference to be in the bottom 25%, the top 36%, whatever they happen to be the numbers? Wouldn't it just be a matter of adding up various combinations of these till you got to the total that they mentioned? And that's probably the second most difficult question in that chapter. But that's how you're going to tackle it when you do it. Number 30. And 14 as well. Same questions. Are we good? Last chance, because I'm still in this section, but I'm going to change tack and start doing using salt to do other kinds of questions. Last chance. We good? We're good. Okay. Now, I guess I'll keep that for a minute. This is kind of clunky, isn't it? An awful lot of work just to get, what value does this, what value does that, right? Wouldn't it be nicer if we could find a way of answering this question? So imagine that I pick a nice easy one, the IQ one again. Let's suppose that the average IQ is 100 and that the standard deviation is 10, right? So there's 110, there's 120, there's 130, 90, there's 80, and there's 70. Wouldn't it be good if we could find a way to answer questions like, what percentage of people have an IQ like greater than 117, right? Just a random number, or less than 93, or have an IQ between, say, 91 and 99. Do you know the kind of questions that you'd like to know quite detailed percentages, right? What percentage of the data, right, is bigger than 117 or less than 93 or between two numbers? And you might think that would be impossible if the only things that you know is that the mean is 100, that the standard deviation is 10, and that it is a nice, right, bell-shaped curve. But the good news is that that's actually all you need. But we don't do a formula. We use salt. So what I'm going to show you now is how to answer questions like this, right, using salt, okay? So click this guy out, eventually. Click back in, and let's have a look at the question that I'm talking about. Here are various questions doing the same types of things, right? They have a Z-score, and then they have a thing called the approximate proportion. Well, you think of approximate proportion as just mean the percentage answer, right? But instead of writing the answer as a percent, you write it as a decimal. And that's just because that's the way salt works. So can you imagine the proportion 0.17 just means 17%, right? The proportion 91 means 91%, right? So that's fine. Can't we turn decimals into percentages dead easy in our head, right? So we're just going to do proportion. So whenever you see the word proportion, you're going to write in the answer as a decimal. If it says percentage, you're just going to turn that decimal into a percentage. So I'm going to hit the salt button. Okay, do I need it here to click on that? I do, good, I figured it out. I know last time I spent ages moving windows around. Right, so you hit the salt button and this thing appears. So far, so good. Now, don't know what that's about, but that doesn't matter right now. I'm going to have to shrink this picture down because there's a lot of information in and you can't see all. There we go. Can you see my nice pretty hill that I drew? Right, normal distribution. When you are doing this, make sure that your setting says normal distribution. If you click on this, you see there's all sorts of other pictures that we don't want. Make sure it's a normal distribution. Now, in the story that I've got, the mean IQ was 100. So you type in 100 here. Does that make sense? You would have to do that. Then you go over here and the standard deviation is 10. So you put 10. And there's going to be numbers floating about because who knows what the last question is. My first question was greater than 117. Now, do you notice in this picture, greater than is called right tail? Can you see that's bigger than? A less than will be called a left tail, because if you're doing less than something, you take that button. If you're doing bigger than, you use that button. Which of these two do you think you're going to do when it's between 91 and 99? I think it's kind of obvious, but which do you think you should use?
Left tail.
Oh, if it's a between two numbers.
Oh, between.
Yeah, that's the only one that makes sense because the word almost is what you do. Right, let's go back to the first question. The first question was greater than 117. So greater than, and then you go here and you type in 117. Now, do you see that number that's here? That's the proportion. Roughly about 4% of the people, well, 4.4% of the people, right, would have an IQ greater than 117. We cool with that? So I go back here. Oops, no, I don't. Oh, there we go. I go back here and I type in 0. How much decimal places do they want? Okay. I'm going to type in what I want because they didn't tell me how many they wanted. So how about 0.04, a couple more digits, 46 there. That's what I'm writing down. Actually, why not just write everything down that way? I don't need to worry about rounding off. Right, I just write my answer down. And what's the Z-score? Well, if I bring this picture back, what's the Z-score? Oh, can you see it's there? So 1.7. Do you feel comfortable about how this can be used to calculate these kind of things? Right, let's bring this picture back. Right. I would like to know what percentage of people have an IQ score less than 93. Right, less than is a left tail. Can you see the shading helps? And I want it to be less than 93. So I'll change this number to 93. And I'll rub out all this other stuff because that's not my number. Right, can you see this time the answer is about 24% of the people, 0.24. And the standard deviation is negative 9.7. And I also want to know what percentage of people have an IQ between 91 and 99. So here's both tails. Right, there we are, they're between. And I want on one side, I want 91. And on the other side, I would like 99. And the answer is about 27, 28% of the people. So if the only thing I know is the mean, the standard deviation, The mean, the standard deviation, and that it's got a nice symmetric shape. Can't we find percentages of all sorts of things? So let me zoom back to the picture and tell you how things like this can be used. Do you know that sometimes some of you maybe have already done this, that you get SAT scores and all the other kind of college, was it REC or CRE or whatever they're called, right? And you get a score, and then you sometimes get a thing that says you're the 93rd percentile or something. You remember if you've seen that, it's the kind of thing. What are they talking about here? Well, imagine that there's an exam. So you have to sit this exam, and the mean of this exam was 150. Maybe the exam's 200 points, right? And that the standard deviation of this exam was 21. And you got a score of 181. So if you imagine what my picture would look like, there's 150, there's me, I'm 181. Wouldn't you like to know what percentage of the people did worse than me? That's kind of pessimist way of looking at it, right? Or maybe the optimist way of looking at it. Right, if you want to do that, don't you just go into that salt, which I'm going to do without you seeing me doing it. And I'm going to go in and I'm changing the mean now to 150. And I'm changing the standard deviation now to 21. And I want everybody, oh, by the way, can you see that if you want this, can you see that is a left tail? You see the terminology, right, to the left. So I'm doing a left tail, and I'm putting in 181. Any gut feelings about how good that is? Do you think that's going to be a really big number? You know, like 90% of the people did worse than you? Was it only 60%? Any gut feelings before I tell you what it is?
Absolutely a big number.
Okay. The answer to that, right, is the percentage. So I'm converting into percentage. It's that fella, which is 93%. So you would be in the 93rd percentile. That's just the jargon way they would say it. So you should be pretty happy with yourself. Wouldn't that mean you did better than 93% of the class? Isn't there only 7% of the class better than you? Agreed? Now, suppose I went and told you that there were 40 people in the class. Then you could even find out what position in the class you were in. Because wouldn't you be roughly 30%, 39%, 40? And if you do 39% to 40 and you round it off, it's about, you were 37th. So you were 37 out of 40 people. So only 3 people in the class did better than you. Isn't that quite a cool thing to be able to calculate? And you could do anything. Couldn't you find out, you know, for a different score, how many people got less than this score? How many got more than this score? How many got between 20 and 50 points? How many got between 100 and 190 points? SALT does all the number crunching. All you got to do is make sure that you write down exactly, you know, put the numbers in the right place and choose the right thing. So I'm going to introduce you to some terminology. If I wanted to find the proportion of people with a score, and what was it in this case, less than or equal to, say, 181, we would write it like this: P for proportion, X less than or equal to 181. Would you agree that's a much more condensed way of asking the same thing? Are you comfortable that this notation is just a shorthand for this? The proportion of scores, in this case, less than or equal to 181. What would this mean in English? What would that mean in English?
The proportion is more than 190.
Agreed. This is the ugliest of the three. I think most people are happy less than 181, more than 190. This is the proportion one that gets people. What does that notation mean in English?
X be between 145 and 155.
Correct? Or just the proportion of people who get scores between 145 and 155. If you said it in even more English, you're right, Laura. In a way, isn't that the three most obvious things you could ask? And that's the three that we typically ask you. Right. Any questions about that? Are we comfortable?